All right, Calc 12. This is inverse trig derivatives. Good times. The last of the trig derivatives. Again, I would normally do this in class. I'm making this optional this year just because of timing, and I want to get on to exponentials and logarithmic functions and then a little bit of antiderivatives just so you have a taste in your mouth before university. But this could be there for university times. That's why it's on YouTube for your future. You can look at this when you're 30 years old or when you're 80, when I'm long gone. All right, we'll talk to you, well, right now. What am I doing? Okay, here we go. Thought I was done. Here are 3 facts that you need to know. So, I'm going to prove one of them. The other 2 can be proved similarly, which I'll leave that up to you if you have time. So, the derivative of inverse tan is given by that function there, 1 over the square root of 1 minus x squared. The derivative of inverse cos is negative 1 over the square root of 1 minus x squared. And the derivative of arctan is 1 over 1 plus x squared. Just to make sure you're aware of where and how and why, I'm just going to get rid of all of this for a second here. So there's our inverse sine function. Its derivative, I'm just going to zoom in, boop, I'm just going to go over here and I'm going to call this function f of x just for the computer purposes. I'm just going to Desmos. I'm going to go down to the functions. Whoopsie daisy. And I'm going to pick miscellaneous, derivative, and I'm going to graph the derivative just so you can kind of see. So there is the derivative of arc or inverse sine. You can see the slope is always positive, and it goes from quite steep positive to the least steep right here, and then back to steep again. That's why it's high, comes down to a minimum slope if you want, up to there. And that function, notice, it doesn't tell me what it is, it just graphs it for me. If I type in 1 divided by the square root of 1 minus x squared, you can see that is that function. So I'm not making this stuff up. All right, let's prove why that is the derivative, and then we'll take derivatives with these functions. All right. Oops, there we go. So these are the last of the derivatives you need to know. Here's a proof of why the derivative of inverse sine is this. Here's their proof. We're going to let f of x equal inverse sine. What's the derivative? Obviously, that's our goal. Remembering that I'm going to let f of x be y for no particular reason. Remembering that the output of inverse sine is between negative pi over 2 and pi over 2 in these 2 quadrants. Important fact. We're going to rewrite this because we don't know this function's derivative at all. We're going to rewrite this as x equals sine y. That's just the inverse writing of this, or writing it in a different form. Remember, this is the ratio. Y is the angle in this form. So we're going to now take the derivative implicitly because we know the derivative of sine. So derivative of x is 1. Derivative of sine y with respect to x is cos y dy dx, not a t. What am I doing there? We're not doing related rates. That's also dx. Sorry about that. Caught my own mistake, but that's good. Okay, so one thing to take note of is there's the implicit. Solving, you get dy dx equals 1 over cos y, which notice looks nothing like what someone said it would be. What someone noticed, though, and it's interesting because they wanted to get this in terms of x, they noticed this. If I drew this angle in quadrants 1 and 4 where it could be, this represents the angle. So there's the angle y right there. The next thing is, this is the ratio. This is x over 1. This is your opposite. This is your hypotenuse. So the hypotenuse of this is 1, either here or here, depending on what quadrant you're in. And the opposite side is the x. I've drawn that wrong, actually. Let me redraw that. I don't like that. That's drawn backwards. So let me draw it in quadrant 1 first. So here's angle y. The opposite side is the value of x, which is counterintuitive to your thinking, but remember, that's just what it is. That's the opposite, and this is the hypotenuse. Hence, this side here with Pythagoras is 1 squared minus x squared. If I had drawn it in the fourth quadrant, because I don't know which quadrant I'm in, that would have been angle y, this would have been x, this would have been 1 still, this still would have been 1 squared minus x squared. No matter which picture I look at, cosine of that angle is adjacent divided by hypotenuse. So cosine of y is equal to 1 minus x squared over 1 for both pictures, no matter which quadrant I'm in, so there's no conflict or there's no double answer. So hence I can replace cosine y with square root of 1 minus x squared, and hence that's why that is the derivative of arc sine. So similarly, you can do the same thing for arc cos to get this, and arc tan to get that. Now, keeping these in the back pocket, so I'll fold it over. Now we're just going to take a few derivatives using these last few derivative knowledge facts. So, if I wanted to take the derivative of arc sine or inverse sine of 1 minus x squared, just got to think about this as the outer and this as the inner. And I got to take the derivative by using the outer derivative, and the outer derivative is this, but it has to be evaluated at the inside. So it's going to be 1 over the square root of 1 minus what goes in for the x squared, if you want, is the inside, 1 minus x squared. So there's the outer derivative evaluated at the inside, so the mama. The baby is the derivative of the inside, and the derivative of 1 minus x squared is negative 2x. Now a little bit of cleanup, if I so desire. I don't have to. I could have just left the answer like that as far as if I just wanted the derivative, I'm done. But to make it look better, one thing they may do is they may, because they like it, they may feel like distributing this. So I'll write it out just so you can see it, because this sometimes is the hardest part, not the calculus, but the pre-calculus. They'll distribute this out, possibly, and you end up with, so this would be 1 with a negative up front, negative 1. This would be negative x squared and negative x squared, which would be negative 2x squared times the negative, so it would be positive 2x if I distribute that out. And there I'd have positive x to the fourth with a negative, so it would be negative like this. The 1's happen to cancel, and you end up with 2x squared minus x to the fourth. At that point, you could, if you so desire, good answer, you could factor out an x squared from the bottom. And, interestingly enough, the square root of x squared could be, if you so desire, written as the absolute value of x. So they could have an answer in the back that looks like this, but they probably will write it like that because they like to simplify. Okay, so interestingly enough, you get an absolute value out of that if you want. That's just coincidence. Okay, next derivative is x times inverse tan of the square root of x. So right away I can see, hey, this is a product. And within the product rule, the derivative of that's going to be simple. The derivative of this part's going to invoke a chain rule outer inner. Okay, I might even want to write this with a power of a half if I don't like the way that's written. So now the derivative would be, so product rule would be the first times the derivative of the second. So in a moment we're going to take the derivative of that plus the second times the derivative of the first. Now I should be able to do that. The derivative of x is just 1. The hardest part is this part. So now here comes my chain rule. Here's the part that's new. So chain rule, outer derivative is this. So it's 1 over 1 plus something squared. It's not x. In this case, it's the square root of x, because that's what the inside is. So there's the outer derivative evaluated at the inside times, now I need to multiply by the derivative of the square root of x, and the square root of 1/2 x squared, you've done it many times, is this, 1 over 2 root x. and doing a little bit of cleanup. Square rooting x and then squaring is just x, so I could write it as, this would be just 1, sorry, plus x, and then there'd be a 2 root x here, which I could, that square root of x could divide into there, so I could, if I so desire, I don't have to, I could write it like this. There's my answer, or one particular simplified version of it. But that's right, that's right. This is not technically right because you haven't done it yet. I mean, it's not wrong, but it's not done. This is done. This is done. This is done and simplest. Okay, next guy. And the last one, I think. Is it? Am I lying? Oh no, we got a sec. So 2 more. So the derivative of, so sketch the derivative of that. Okay. So to sketch the derivative, well, I have to take the derivative. So let's practice our derivative taking skills. Derivative of arc cos, and this is the in, so this is the outer, this is the inner. Derivative of arc cos is negative 1 over the square root of 1 minus x squared, but the x is sine, so it's sine squared, times the derivative of the inside, and the derivative of sine is cos, making it look a little prettier. Not much though. I get this, sorry. And then now, how in the heck do I sketch that without Desmos? So let's think about it for a minute. If I really had no clue, I could do an XY table with a calculator, but in all honesty, if I had a calculator, I might as well just do it on Desmos anyway. So something of interest here. Sine squared plus cos squared equals 1. Hence, 1 minus sine squared is equal to cos squared. So I could replace this with a trig identity of the square root of cos squared. That's interesting. Square rooting a square is the same thing as the absolute value. That's interesting. Then, okay, wow, weirdness. Then you could, if you were really witty, you could say, well, depending on what's happening here, these will divide out, but piecewise in a sense. If you just were, first of all, if this argument in here was positive, so I'm going to put here if cos x is positive, this will end up being positive, and hence you'll get negative 1. If, on the other hand, cos x was negative, you would have negative cos x divided by negative cos x, which would give you 1. So interestingly enough, you get this simple, well, I'm not going to call it simple, simple-ish function, but with really weird restrictions on when this is negative 1 and 1. So let's think about it for a minute. Think about your quadrants. When is cosine positive? It's positive here between 0 and 90, and it's positive here between 0 and negative 90, or 270 and 360, depending on how you want to look at it. So every quadrant 1 and 4 it'll be positive, and every quadrant 2 and 3 it'll be negative. So what does that mean? So let's just think about this for a second. Let me just break this up into the quadrants here. So here's 0. Let's make this pi over 2. Let's make this pi. 3 pi over 2. 2 pi. And you can keep going. And let's go the other direction too, just for the fun of it. Let's see. All right, so awkward, but neat. So where is the graph negative 1? It's negative 1 between 0 and 2, or pi over 2. Now here's got to be interesting though, when it is equal to 0, so at this point here, it's actually an open circle. No, we're good. No, it's at that point at 0 would be 1. Okay, so it's just at negative 90 and 90 where it's open, and then it's also going to be negative 1 here. So that represents between, in these two quadrants, between negative 90 and 0 all the way to 90, it's negative 1. Then from pi over 2 all the way to 3 pi over 2, it goes back to 1. So it jumps up to here. And then it'll jump back down to there and do another period of that, and so forth and so on, like this. And it'll kind of be toggling up and down. Alright? So that's a really interesting graph, actually. Which then, if you actually know that graph of the derivative, you could actually then sketch the original if you use the slope, because the slope's just going from -1 to +1. You actually get like a sawtooth shape or waveform. Just go to Desmos and graph that and graph its derivative. You get some neat stuff. Like really weird facts. Like right now it's like we're dealing with these weird beasts. Those guys that go out in the jungles and look for those interesting animals. These are the math animals. So here we go. Last one. Find the derivative dy prime or dy dx of this. Because there's a y on both sides, screams implicit. Okay, plus also what I see here is there's going to be a chain rule, outer, inner, and I also see quotient rule. So lots of stuff happening here. So let's take the derivative of both sides. Dy dx, and we'll take the derivative of this side. This side, dy dx, that's done. Over here though, chain rule. Outer derivative. So the derivative of arctan or inverse tan is 1 over 1 plus the argument squared times the derivative of the inside, and that is quotient. So the quotient rule is of this would be bottom times the derivative of the top x, which is 1, minus the top times the derivative of the bottom, which is dy dx, all over the bottom squared. And unfortunately, there's a dy dx on both sides, so we have to manipulate this to isolate it. Unfortunate. So, a few things I would probably do. This looks like a horrendous mess. Don't like it. I'd probably write this as y squared plus x squared over y squared by getting a common denominator of y squared and y squared. Over here, yeah, I'm just going to get this looking better first. There's lots of stuff I could do, but I'd probably do the reciprocal of this. So I haven't done much actually. I'm just playing with this as I'm thinking about what I would do. Oh, I see one thing nice. Y squareds cancel. I'll take that as a gift. I would then probably distribute this out because I need to get this out with me. So I'd end up with y over y squared plus x squared minus x dy dx over y squared plus x squared. Could have cross multiplied too, I guess. I can move, you know what, maybe I will. Let's multiply, I don't like those big clumsy fractions. Let's multiply everything by y squared minus or plus x squared. So I'd end up at y squared plus x squared times dy dx equals y minus x times dy dx. Let's move this clump over to here. Now, if I move this clump over to here, I can write it like that. Because it's already a dy dx term. If I'm adding this over, it's just going to be like it was distributing in, and then I'm one baby step away from having dy dx. It's going to be y divided by this mess. That's how I would probably handle it myself. Main thing is, can you get to there? Because right there, there's your calculus done. There's your pre-calc 11, pre-calc 10 factoring on a high level coming out. Okay, that is it for the video. That is it for Trig. Boo!